Hello everyone, today's topic is diagonalization and eigenvectors. This is a continuation of what we discussed in the last lecture. Just to give you an idea what diagonalization is all about, first of all, let's notice that diagonal matrices are nice in the sense that they're easy to work with, by which I mean multiply. So let me show you an example of what I mean here. So what is a diagonal matrix? Remember, let's just do a little 2x2 example. Diagonal means that I only have non-zero entries on the diagonal. So everything off the diagonal has to be 0. The diagonal entries can be anything they want. They can be 0. I just know that things off the diagonal have to be 0. And notice that if I take d squared, which is d times d, this is easy because, let's do this. I get another 2x2 matrix. The upper left corner is going to be 5 times 5 plus 0. And then up here I'll have 5 times 0 plus 0 times 3, so this is 0. Similarly here I have 0 times 5 plus 0 times 3, 3 times 0, this is also 0. The lower right corner is what? 0 plus 9. And this pattern happens in general, that what I'm going to get here is in the diagonal I'll have powers of the diagonal entries, and off diagonal will again be 0. So in other words, the product of two diagonal matrices is diagonal. And in general, I have d to the k is really easy to figure out. I just take 5 to the k, 3 to the k on the diagonals, 0 everywhere else. Okay. And then, so great, that's so easy. I can take high powers of diagonal matrix more or less immediately. Why can't they all be diagonal matrices? Well, note that this trick works if A is just similar to a diagonal matrix. So remember, what that means is that I can write A as P D P inverse for some P. That's what it means to be similar to a matrix D, is that I can write A as P D P inverse. Then what do I have? Well, I have a to the k, which now by definition is going to be p d p inverse times p d p inverse times p d p inverse dot p d p inverse. And what do I get here? Well, every time I concatenate another p d p inverse, I get this p inverse times p, which of course is the identity. I get another identity there, there, there. And then what's going to happen is, well, those all become the identity. So now I'm just multiplying d times d, another identity, so times d. You can kind of think about, collapsing the telescope. What this becomes is just p times d to the k, p inverse. And the point is that if d is diagonal, well, we just saw that this is easy to calculate. Okay, so we turned this a priori complicated computation, a to the k, to just basically 3 matrices multiplied together, because d to the k I can just immediately write down. So even if this is like a to the 100, I just have to more or less calculate 3 matrices. Let me just give you an example. So if A is as above, then you can check that, well, let me let P be 1, 1, minus 1, minus 2, which means P inverse, you can check is 2, 1, minus 1, minus 1. And what you can also check is that, in fact, A equals P times B, P times D times P inverse, where D is as above. So what was D up here? It was 5, 0, 0, 3. Okay, so with these choices of P, I can write A as a matrix times the diagonal times that matrix inverse. And what do you have here? Let me just do this again. So what is A to the K? We just saw that if you write A as P D P inverse, that means A to the K is P times D to the K P inverse. And let's just go through this calculation. So what is this? P was 1, 1, minus 1, minus 2. D was this, times P inverse. Let me just, to illustrate this at least once, let me go through this calculation. This is 3 matrices multiplied together. So maybe I'll first do this here. What I get is, so I'm missing a to the k here. Okay, that was of course important, that d to the k, as we know, is given by 5 to the k, 3 to the k on the diagonals. So now I multiply these first 2 matrices, I get 1 times 5 to the k plus 0, so this is 5 to the k. Then I get 0 plus 3 to the k here, and I get minus 5 to the k, and then a minus 2 times 3 to the k, multiplied by this matrix 2, 1, minus 1, minus 1. And just for the sake of completeness, let me multiply this out. It's a little bit messy, but we'll see it's, pretty nice considering that we're getting a formula for a to the k. So this will be what? 2 times 5 to the k minus 3 to the k. This entry will be 5 to the k minus 3 to the k. And here I've got a, what is this? This is a minus 2 times 5 to the k, and then a plus 2 times 3 to the k. And finally, this entry is going to be 2 times 3 to the k minus 5 to the k. Okay, so again, for any integer k, if k is 100, I can take a to the 100, and it's just this. Plug in 100 and you get the answer, which is, I think pretty nice. It's a compact formula for arbitrary powers. Okay, so what's the punchline here? So punchline is that if A is similar to a diagonal matrix, say D, and what that means is that A equals P, D, P inverse for some choice of P, then A to the K is easy, to calculate. So that motivates the following definition. Well, we say that an n by n matrix A is what's called diagonalizable if this happens. So if it's similar to a diagonal matrix. So this is not always going to be the case, but we'll see that this is something that's desirable, and we'll explore kind of the situations where we do have such a thing. And let me just be more precise here. So i.e., there exists, what does it mean to be similar to a diagonal matrix? There exists an invertible matrix P such that A equals P, D, P inverse. And let me just emphasize, this has to be invertible. Okay? So what you should be thinking now is, okay, that's great. We just saw an example of how that leads to some nice applications, but how the heck do you get P, right? I mean, so you've given me this matrix A, and I want to know, is it similar to a diagonal matrix? That means I need to find a diagonal matrix D, but even more, what is this P going to be? So how do we find these matrices P and the diagonal matrix D if you just give me A, right? It seems like completely mysterious right now. And here's our main kind of theorem for the day. This is the main kind of connection to what we've been talking about. So it turns out that an n by n matrix is diagonalizable, so it has this property if and only if A has n linearly independent eigenvectors. Okay, so again, we're saying that a matrix is diagonalizable. That means it's similar to a diagonal matrix. That happens if and only if you have kind of, in some sense, a lot of, well, the most you can have linearly independent eigenvectors. And what more is true is that, in fact, the eigenvectors you get, so if you happen to have a collection of n linearly independent eigenvectors, so call them v1 through vn, these will can be taken to be the columns of the matrix P. So you take those vectors v1 through vn, you just make them into the matrix P, and then and D will then be, right, so this has to be a diagonal matrix. We need to have, what is a diagonal matrix? It's determined by the entries on the diagonal. So we have some we need n numbers to put on the diagonal, and we have those coming from the given eigenvectors. So this is where lambda I is the eigenvalue of VI. Okay, so let me just, that's our main theorem. This is something that we'll talk about for a couple lectures now. But let me just show you kind of how that works with the example we just did. So just going back to this example, so from above, the matrix I gave you was A, what was it, 7, 2, minus 4, 1. So, for example. Now, we're going to kind of reverse engineer what I just did, but it turns out that A has eigenvalues. Lambda 1 is going to be 5, lambda 2 is going to be 3, and this guy has an eigenvector, turns out it has an eigenvector 1 minus 1. This has an eigenvector v2 to be 1 minus 2, so you can check this, right? So for instance, A times v1 is 7, 2 minus 4, 1 times 1 minus 1, which is equal to, let's see, 5, and then a minus 4, a minus 5. So you see that this is actually 5 times the matrix, the vector you gave me, right? So indeed, 1 minus 1 is a eigenvector with eigenvalue 5. Anyway, the point of this theorem implies that what we can do is now take these eigenvectors, put them into a matrix, 1 minus 1, 1 minus 2, and that'll be the P matrix that's going to do the diagonalization for me, with diagonal matrix given by the eigenvalues, so 5, 3. So let me take some color here maybe, and just the, the flow chart here is that the eigenvectors are put into the matrix P, the eigenvalues are the entries of the diagonal matrix. Okay, so, and in the end, the punchline here is that you can check, this is what we basically started out with, our discussion, you can check that A is actually equal to P times P times D times P inverse. Okay, and that's how you get, the P and the D matrix that makes this similar to a diagonal matrix. Okay, so I think that's all for today. We'll continue with this next time. I'll give you kind of a recipe for what's called diagonalizing a matrix. We'll see you then.